position and velocity merge into a hazy concept. Just like the Casimir effect, as technology becomes smaller and smaller, this is a problem that engineers will increasingly have to face. That said, the Heisenberg uncertainty principle is not a mystery. It is a fact. Strictly speaking, it isn't even an uncertainty. It just says that our classical notions of position and velocity do not apply in the very small. Nature works in a different way down there, and we do have theories to account for it, theories that predict it, quantum physics. And these strange effects do carry through to our scales, but we're just not built to feel them. They become insignificant when too many particles are involved. And that is a well-understood fact too. So where is the mystery we were looking for? Is there one? There is. We overlooked something in the measurement you've just made, the quantum wave collapse itself. And that is a mystery. A really puzzling one. When left alone, quantum particles behave as multiple images of themselves, simultaneously moving through all possible paths in space and time. Now, again, why do we not experience this multitude around ourselves? Is it because we are probing things around us all the time? Why do all experiments that involve, say, the position of a particle make the particle suddenly be somewhere rather than everywhere? No one knows. Before you probe it, a particle is a wave of possibilities. After you've probed it, it is somewhere, and subsequently it is somewhere forever, rather than everywhere again. Strange, that. Nothing, within the laws of quantum physics, allows for such a collapse to happen. It is an experimental mystery and a theoretical one. Quantum physics stipulates that whenever something is there, it can transform into something else, of course, but it cannot disappear. And since quantum physics allows for multiple possibilities simultaneously, these possibilities should then keep existing even after a measurement is made. But they don't. Every possibility but one vanishes. We do not see any of the others around us. We live in a classical world where everything is based on quantum laws, but nothing resembles the quantum world. So the question is, how can we make quantum effects appear at our human scale, so that we can probe them and see the collapse, if there really is any, with our very eyes? Is that possible? And if one could see quantum effects like this, what would we expect to see? In 1935, 2 years after being awarded the Nobel Prize for his work on quantum physics, Austrian physicist Erwin Schrödinger devised an experiment to bring quantum effects to our scale. It involved a cat and a box. Even though it was only ever a thought experiment, no scientist has stopped wondering whether that cat is dead or alive ever since. You are about to do Schrödinger's experiment again. And I hope you're not too fond of cute, purring, innocent, playful kittens. There is a good chance the cat will be harmed during the experiment. In any case, do please keep in mind that the idea here is to make quantum effects appear macroscopic. Some sacrifices may be necessary. With that disclaimer behind us, let's start. For those of you who do not know, a cat is a four-legged, usually furry, tailed mammal which lives within the same scales of reality as we do. Most people like to cuddle them, but not all. They come in pretty much all colors but, as far as I know, not in green. To perform Schrödinger's thought experiment, you decide to pick an adorable little kitten, black and white, and you look for a box that can be so perfectly sealed that, once closed, no one can know anything about its interior from the outside. Besides the cat and the box, you need to fetch a radioactive substance, a very special one that is known to have a 50% chance of emitting some radiation during the time of your experiment. Radioactive materials are very unpredictable. According to quantum laws, there is no way whatsoever to know in advance whether they will decay and emit some radiation or not. There is just a probability. 1 chance out of 2, for the substance you've found. Now, you also need to find 3 other objects: a radiation detector, a hammer, and a vial containing some very lethal poison. Then you link everything together so that if the detector notices some radiation emitted by the radioactive substance, the hammer breaks the vial and the poison is released. This would be harmless were it not for the fact that you put all of these things, the hammer and the radioactive substance and the poison and the cat, in the box and seal the lid. Then you wait. What then? There is a 50% chance that the cat gets poisoned. Everything depends on the radioactive decay. A twisted experiment, agreed. You definitely should not try it at home. Now, here comes the question, is the cat dead? Quantum effects are in progress here, as desired. And the outcome is macroscopic, big enough for us to see. But without opening the box, there's no way for you to know whether the radioactive decay occurred or not, so there's no way you can tell whether the vial is broken or not and hence whether the cat is dead or alive. Nothing new under the sun, you think? Well, with all things quantum, one ought to be vigilant and use common sense sparingly. Or indeed not at all. To infer anything down there, one needs to abide by the laws of the quantum world. In real life, one could expect the cat in the box to be dead or alive. But then both those answers would be wrong. In the quantum world, what can happen happens. You should be used to that by now. Here, the decay and the non-decay of the radioactive substance can happen with the same odds, so both do happen. Just as a particle can travel to the left and to the right of a solid post simultaneously, radioactive decay also simultaneously happens and doesn't happen, as long as no one looks. As said above, most of the time such a superposition of possibilities goes unnoticed by us because, for some unclear reason, it never occurs at or reaches our scale. In our particular experiment, however, the setup is designed so that our eyes can see it. The simultaneity of 2 quantum possibilities is directly linked to the rather dramatic death or survival of a cat. So what do the rules of the quantum world say? They say this: the decay and non-decay events being directly linked to the poison, the cat, as long as the box is not opened, should be neither dead nor alive, but both. Before you open the box, the decay has both occurred and not occurred, so the poison has been released and not released. So the cat is dead and not dead. Dead and alive. Hearing this, you immediately open the box to check it out. The cat jumps out, unharmed, and so very cute. And there's no carcass lying at the bottom. You scratch your head. This whole business of superposition of states and subsequent collapse of quantum possibilities suddenly sounds like a pretty elaborate trick rather than a real phenomenon. Did we get it wrong? Was the cat really dead and alive for a while, or was it all a cheat? Let's see. Opening the box made you interact with the experiment, right? Aha. So you did interfere. You did look. And when one looks, nature has to choose. So the choice, the collapse, if real, must have happened, leaving the cat alive. 48. But did the cat's fate freeze before you opened the box? Or did it do so after, extremely quickly? You are back to the initial question, did a collapse happen at all? Schrödinger devised this thought experiment in 1935 and, for years, no one could answer his puzzle until French physicist Serge Haroche and US physicist David J. Wineland managed to devise a real experiment able to detect the very superpositions that were then supposed to collapse. They did not use a cat, though. They used atoms and light. And they saw that quantum superpositions are very real, that pretty much any quantum particle can, and does, simultaneously exist in different, mutually exclusive states. Today, this is actually the basic reason why engineers are trying to build quantum computers. Using the ability of quantum particles to be in different states at once, computers can, in principle, become exponentially more powerful than what can be achieved with our classical ones, making parallel computations simultaneously. Heroche and Wineland jointly received the 2012 Nobel Prize in Physics for this. They somehow proved that Schrödinger's cat really was both dead and alive, simultaneously, at some stage. Now, where is the mystery here? It has to do with what is gone. The superpositions are real, fine. That's what Heroche and Wineland proved. We have to accept it. But when you opened the box, when the collapse occurred and the live cat jumped out, where did the possibilities you did not see go? Since it must have been real at some stage, where did the dead cat go? That is the mystery. Many scientists have wondered about this, and a few putative answers have recently begun to flourish. Some guess that the possibilities that were not observed fade away, like drops of ink within a lake, the lake here being the world we live in, as if pearls of unfulfilled possible realities diffused within the one and only reality that prevails, the one we are part of. Some others believe that our consciousness has something to do with it all, that it is the very act of experimenting or even thinking that freezes reality in one state, thereby creating it. And then there is U.S. theoretical physicist Hugh Everett III. Born in 1930, Everett was a very strange man. Extremely bright, he studied mathematics and chemistry and physics to eventually write a PhD thesis under the supervision of one of the most influential U.S. physicists ever, John Archibald Wheeler, from Princeton University. Everett gave up physics right after his PhD, though, mostly because he apparently believed it was all too weird. Wheeler's failed attempts to have his students' ideas taken seriously by the scientific community probably didn't help either. At 21, leaving theoretical matters behind, Everett began to work for the top-secret weapons branch of the United States military and eventually died of too much drink and too many cigarettes. In an uncanny resemblance to the lives of some famous poets or painters who silently burned their talent in their early years while held in contempt by their peers, Everett's 1956 dissertation later became a classic. In it, he made the extraordinary claim that since quantum ideas were working so well at very small scales, they should be taken seriously all the way through to our scale. Everything in our universe being made of quantum stuff, everything should therefore be thought of as a huge quantum wave of possibilities existing simultaneously. With such a point of view, no collapse then ever occurs. Every possibility exists. With such a point of view, the whole universe branches off every time a choice has to be made as a result of an experiment or anything else. Unfathomably many parallel universes should therefore exist, where all the possibilities, all the alternative outcomes, are facts. According to Everett, parallel histories should surround us. You hesitate between two elevators before picking one? Another you, in a branching parallel universe, chooses the other. In another one, you hit the wall in between the two. In yet another one, you take the stairs. All possibilities are thus fulfilled. In a way, Everett's literal understanding of quantum physics says that if you put selfishness aside, you should never be sad. Whenever something bad happens to you here, infinitely many parallel yous and infinitely many parallel universes escape the bad news and feel happy. Everett is still alive and even reading this book in yet another infinity of these parallel realities. In some he likes what I write about him. In others, he doesn't. In others yet, he actually wrote this book himself and, in it, Schrödinger's cat is a green dog. According to Everett's interpretation, no real choice is ever made by nature. All possibilities happen. You just do not know about it. No wonder he gave up physics. Everett's idea is weird indeed, but it has now been taken seriously by some of the greatest physicists of our times, with many mathematical models pertaining to the origins of space-time making use of it. There certainly is no experimental confirmation in sight for Everett's claim, but it is an appealing reason why the reality we live in is not a superposition of quantum possibilities. The possibilities we do not experience are real enough, but elsewhere. Now, while you get used to this idea, let's quickly summarize what you've been through up to here. Since the beginning of your journey, you have been traveling within the very big and the very small separately. Shooting through cosmic kingdoms, you have discovered what the large-scale structure of our universe looks like and how it is ruled by general relativity. In the realm of the tiny, you've seen that the quantum rules of nature are different from the ones we are used to in our everyday business. Until this part, you have therefore been traveling throughout what is known, both theoretically and experimentally. You've seen what the universe appears to be, whatever the scale, from the point of view of an early 21st century scientist. In this part, you've started to glimpse the limits of this knowledge. You've seen that not only are general relativity theory and quantum field theory reluctant to talk to each other, the quantum laws do not appear to rule our daily lives, for reasons that may, for some, go as far as involving the existence of parallel worlds. You'll see even weirder things in Part 7. For now, however, let's continue to exercise your mind and leave the very small to get back to Einstein. What about his theory? What are the mysteries that can be found there? Are there any? Are they as ubiquitous as the infinities that mar quantum field theory? To both these last two questions, the answer is yes. For dark matter. Forget about cats and dogs and parallel universes of alternative realities. Forget about the quantum world. Forget about your mini-you. You are now in space, as a mind. You've seen that the very small is filled with mysteries and you intend to check if Einstein's theory works everywhere, or if it too has shortcomings even without trying to turn it into a quantum theory. So you are in space. The Earth is behind you and you fly forward. You pass the moon, the sun, the neighboring stars. Up to here, Einstein's theory of gravity works perfectly. Stars and planets move as they should. You head out of the Milky Way, into the intergalactic medium, where you stop. The Milky Way is beneath you, just there. Other galaxies shine in the distance. Huge spirals with hundreds of billions of stars that radiate light in an otherwise dark universe. From what you've learned about gravity, you know that, just like the planets around the sun, the velocities of any star within a galaxy can't be random. Stars that fly too fast should escape their galaxy's shelter and forever wander, lone shiners, through the immense distances that separate galaxies from one another. Were the stars to move too slowly, they'd fall down the space-time slope created by all the other stars, a slope that would effectively make them move towards the galaxy's core, the central bulge full of stars, where they'd end up being swallowed or destroyed by the giant black hole that patiently preys there. Without the right velocity for it to stay in a stable orbit, a star is either out of its galaxy, or it is doomed to fall, just as a marble spinning in a salad bowl either falls down or is ejected. You remember that Newton's gravity failed when gravity was too strong. Near the Sun, his equations required corrections to account for Mercury's drift. Einstein found these corrections by revolutionizing our vision of space and time. And now, 100 years later, it is Einstein's turn to face a change of scale. What about Einstein's gravity around whole galaxies? Does his theory of space-time curves work when faced with hundreds of billions of stars rather than just one? That is what you are about to check. You take out a stopwatch and start timing the stars as they travel throughout the Milky Way. To survey 300 billion of them at once is tricky, so you start with the outskirts, around the tip of one of the magnificent spiral arms, far away from Sagittarius A, our very own supermassive black hole. You count 10 seconds. The star you were timing traveled 2,500 kilometers. Not bad. That corresponds to an average velocity of about 900,000 kilometers per hour around the center of the galaxy. Not bad at all. Its neighboring stars are just as fast. In fact, any two stars that are the same distance away from our galaxy's core have the same velocity, the slowest ones lying further out, while the fastest, like the speedy S2 you encountered a while ago, lie deep within. And if you wonder how long it takes one of these outsiders to complete an entire run around the Milky Way, the answer is about 250 million Earth years. A long journey. The Milky Way is big. The Sun, being a bit deeper inside, travels around the Milky Way in slightly less than 225 million years, a period called a galactic year. The last time the Earth was at the galactic position it has today, the dinosaurs still had 160 million years to live. Using such terminology, the Big Bang occurred about 61 galactic years ago, and if we start from today, after 20 more rounds the Milky Way and the Andromeda Galaxy will be so close to each other that they will start to collide. Incidentally, the Sun will explode a few galactic months later. Put like that, it doesn't sound that far off. All right. So far, so good. There doesn't seem to be any problem here with Einstein's theory, except that there is. To be honest with you, you are not the first one to check out how fast these stars shoot around our galaxy. Their velocities have been known for quite a while, since around the early 1930s, when Dutch astronomer Jan Oort measured them. But Jan Oort went a bit further. First, he estimated the amount of matter contained within the entire Milky Way. Then he checked whether the velocities he observed agreed with what was expected, for the stars not to fall in or shoot away. They did not agree. They did not agree at all. Being up there, above the Milky Way, you can check it for yourself. Adding the mass of every star and dust cloud and everything else you see belonging to our home galaxy, you reach the same puzzling conclusion: there is definitely not enough matter to keep any star from shooting away, given their velocity. And unlike the mismatch between Newton's theory and Mercury's orbit, the gap here is not tiny at all. There should be 5 times more matter than what you can see. Otherwise, the stars should all be shooting away, including the Sun. You must have overlooked something. And so must Oort. It's not just a few 100 million stars and their dust equivalents that are missing, or you could have blamed yourself, or Oort, for poorly estimating the whole thing. That would have been acceptable, by the way. But 5 times the amount? What is going on? And who was this Oort in the first place? Can we trust him? We can. He was not just a common astronomer. In fact, his incredible insights helped mankind figure out a lot of what you saw while traveling through the solar system and the Milky Way in the first part of this book. He is, for instance, credited with showing that the Sun is not at the center of our galaxy. He is also the man who hypothesized the existence of the huge reservoir of comets that now bears his name, the Oort cloud, which he crossed at the outer edges of the solar system before entering the gravitational realm of the red dwarf Proxima Centauri. Oort was no ordinary scientist, then, and in 1932, to explain the absurd mismatch between the matter he could see throughout our galaxy and the velocity of its stars, he made an amazingly bold assertion. He stated that an unknown type of matter filled the Milky Way. A type of matter that had not yet been detected in any form whatsoever, neither here on Earth nor anywhere else, because it did not interact with light, making it impossible for anyone to see it with any type of light-gathering telescope. He called it dark matter. According to Oort, dark matter's visible effects are only indirect, through gravity. Dark matter cannot be seen, but it bends space-time like ordinary matter, even though ordinary matter it most certainly is not. It cannot be made out of the same particles that make up everything we know, otherwise we could see it. Such a discovery may sound too big and exciting to be true, and however good Oort might have been, no one is perfect. He might have made a mistake. To check it out, you decide to look at other galaxies to see how they move around each other, just as Swiss astronomer Fritz Zwicky did about a year after Oert's initial claim in 1933. Were dark matter to be real and present and gravitationally active not just within the Milky Way but also inside and around other galaxies too, it wouldn't just modify the way stars move within the galaxies. It would also affect the way galaxies move around each other. So you stare at them, focused. You analyze the spectacular cosmic dance of these immense gatherings of shining stars and you can doubt no more. Just like Zwicky, you are forced to admit that all the galaxies move far too fast around each other not to hide an enormous amount of gravitationally attracting dark matter. And dark matter is not matter. It is not antimatter. It is something else. No one knows what. Many other tests have been done since the 1930s and they have all reached the same conclusion. Dark matter is there. It exists. Everywhere there is matter there is dark matter smeared around. And even though I've tried, throughout this book, to show you everything I wish to share with you about our universe, at this point I have to admit that I can't bring you any closer to it. Why? Because even today, more than 80 years after Oert's bold guess, we still don't have a clue what this dark matter is made of. We know it exists. We know where it is. We have maps of its presence within and around galaxies throughout the universe. We even have stringent constraints on what it is not, but we have no clue what it is. And yes, its presence is overwhelming. For every 1 kilogram of ordinary matter made out of neutrons and protons and electrons, there are 5 kilograms of dark matter, made out of who knows what. Dark matter. Unexpected gravitational mystery number 1. It could mean that Einstein's theory doesn't work at such scales, just like Newton's didn't work too close to the sun. But many independent checks have been made. Dark matter does indeed seem to be everywhere, around galaxies, around our very own Milky Way and throughout the universe, and you can't see it. There seem to be many more invisibles in our universe than there are visibles. 5. Dark energy. Over the eons that passed after the dark ages of our universe, many galactic collisions occurred, entire galaxies clashing and merging. Violence, in outer space, is everywhere, and the galaxies you are now looking at are just the visible part of it. Dark matter, overwhelming matter 5-1, cannot be seen, and yet there is so much of it that it must have played and still be playing a role in this cosmic waltz you are witnessing. A waltz whose dancers, you now know, are gatherings of stars wrapped up in invisible cloaks made of dark matter. The more you watch all these galaxies move around, the more dancers and shapes you see, the more worlds you start imagining out there, with skies completely different from ours. And you suddenly start wondering if some faraway civilization has already found answers to our human queries. But you freeze, blinded. A very powerful source of light just hit your eyes. You peer into the night to spot where it came from, but it is gone. Just as suddenly, though, another one hits you, coming from some other, unimaginably distant place. And another still. Snapping out of your reverie, you focus your thoughts on the galaxies these light signals seem to originate from. Without you knowing why, your heart is racing like mad. You look at their light, at the way they recede into the distance while moving around one another. Something is wrong. The galaxies these lights are coming from are not receding the way they should. We're not talking about how they swirl around one another here, but about the expansion of the universe, about how all galaxies recede into the distance, like poppy seeds in a rising cake. Considering what you've learned about this expansion, these galaxies are not moving right. This is unexpected gravitational mystery number 2. And it involves much, much more hidden energy than dark matter. To understand it, you need to know how to estimate distances in this universe of ours. When you were lying on your tropical island beach, just before you started your journey into outer space, how could you tell which star in the night sky was close, and which one was far away? Brightness obviously isn't enough. Stars come in pretty much all sizes and their actual luminosity can differ a great deal. A bright star, as seen from Earth, could be huge and very far away, or rather small but much closer. Some other trick must be used and, historically, scientists have come up with 3 different tools to estimate cosmic distances. The first one concerns any object, be it a planet or a star, that is quite close to us. It is the easiest one of them all and uses common sense. There's nothing quantum going on here, so common sense is allowed. Picture yourself looking at a tree through the side window of a car on the motorway. Trees close to the road pass quickly by, while ones that are further away seem to move at a much slower pace. Mountain ranges, above the horizon, sometimes seem not to move at all. They can be used as a fixed background. In space, the same concept applies. As the Earth orbits the Sun, objects that are close by have an apparent motion that is rather obvious against the background of very distant stars, which seem fixed. Checking how much an object's position changes against that background while the Earth shoots around the Sun allows scientists to determine how far away in space that object is. It involves mathematics that Euclid would have understood more than 2,200 years ago. It works very well for short-range estimates within the Milky Way, that is. But it doesn't work for determining galactic distances. Galaxies are just too far away. As you, on Earth, orbit the Sun, your perspective on the cosmos can change by as much as 300 million kilometers from summer to winter, but that is not enough to see them move. Galaxies are still part of the fixed background. To guess where they are, you need trick number 2, which involves a very particular type of star called the Cepheids. Cepheids are very bright stars whose lights oscillate between a maximum and a minimum level of intensity with impressive regularity. Amazingly enough, scientists have figured out a way to link this oscillating period to the total amount of light they shine. And that is all they need to tell how far away they are. Just as the sound of a horn dims with the distance it travels from its source, so does light. Harvesting the portion of light emitted by a distant Cepheid as it reaches the Earth hence gives its distance away. And, rather fortunately, there are many Cepheids out there. But this trick has its limits too. To measure the greatest distances in the universe, individual Cepheid stars cannot be used anymore because even the most powerful telescopes cannot tell them from their surrounding groups of stars. To probe the very deep universe, a third trick is needed. You may remember, from part 2 of this book, the work of U.S. astronomer Edwin Hubble. In the 1920s, Hubble became the first person to observe that distant galaxies were all receding from us, that the universe is expanding. Some of your friends kindly confirmed that fact by making night sky observations all around the Earth with their billion-dollar telescopes. In the 1920s, Hubble used the color shift of lights coming from faraway galaxies' Cepheids to figure out their velocity, and he observed that their eagerness to move away from us was proportional to their distance. A galaxy twice as far away as another moves away twice as fast. This law is now called Hubble's law. Trick number 3 involves using Hubble's law the other way round, where Cepheids cannot be singled out from their surroundings. From the way colors are shifted in the light coming from faraway galaxies, scientists can tell how much of our universe's expansion these lights have traveled through. With this, it is possible to tell how far away the galaxy now is. Hubble's law is simple enough and it fits rather well with what is known. Space and time became what they now are some billions of years ago. Space-time has expanded ever since and, as seems normal for an expansion triggered by a violent release of energy, the expansion rate slowed down over the billions of years that followed. Everything is fine with this rather logical setup. Except that it doesn't fit with what you just saw. The bursts of light your eyes caught are at odds with it. The way their colors were shifted does not match the grand, beautiful, coherent picture described above. Something is wrong, and mystery number 2 lingers there, somewhere. To figure out what it is about, let's travel a little and have a look at what triggered the extraordinarily powerful bursts of light that hit your eyes. Starting from above the Milky Way, you head for a particularly beautiful and colorful spiral galaxy lying about 8 billion light-years away. You cross the immense, expanding distances that separate our cosmic family from this other island of lights and, once next to it, you enter it from the side. You fly by millions of its stars, shoot through dust clouds the size of thousands of solar systems combined, and suddenly you stop again. Right in front of you are not one but two shining objects that attract your attention. They orbit one another, very fast, in quite an asymmetric way. One of the two fellows is a huge, angry red star. The other one is bright too, but much, much smaller. About the size of the Earth. And it is rather white. Do not be fooled, though. Despite the huge difference in size, the tiny one is the master here, not the red giant. The small white ball is what remains of the core of a star that exploded a few 100 million years before you arrived. As the star died, as it expelled its outer layers in all directions, its heart got compressed and became what now shines right in front of you. A white dwarf. An extraordinarily dense and hot object. Normal white dwarfs take tens of millions of years to cool off and fade away, eventually becoming cold, dark, lonely space wanderers. This one, however, has chosen a different path altogether. To give you an idea of the density of a white dwarf, let's build a baseball out of different materials. A normal baseball, made out of rubber and leather and air, weighs around 145 grams. The same volume filled with lead would constitute a ball weighing around 2.3 kilograms filled with the densest element naturally occurring on Earth. It is called osmium. A baseball weighs about twice as much again, around 4.5 kilograms. Now, fill the same volume with material from a white dwarf and you get a baseball that weighs 200 tons. Within the kingdom of the extremely dense, white dwarfs are ranked third. Just behind neutron stars and black holes. One could hence expect extraordinary nuclear fusion reactions to take place within them, as within a star, but that is not the case. Unless they find a way to grow, that is. As a matter of fact, white dwarfs remain white dwarfs as long as they contain less than 140% of the mass of our Sun. But this one does have something to feed upon. A star. A red giant. The red giant is being eaten alive, in front of your very eyes. Gravitationally outpowered by the white dwarf's enormous density, the star is doomed. It can't even hold on to its own outer layers. As it orbits the dwarf, its surface is torn off to form a long trail of bright, burning hot plasma that you can see spiraling down towards its greedy dance partner, creating a shining, twisted cosmic river meandering towards the white dwarf's surface, where it is harnessed and compressed. Tremendous energies are at work here. Space-time itself can feel it, just as waves appear around two boats spinning around each other on the surface of a lake. Gravitational waves are being created by the dance of the red giant and the white dwarf, creating ripples that propagate through the very fabric of the universe, altering space and time as they wash over nearby objects. Point 49. And as you watch more and more of the giant star's matter fall towards the white dwarf's surface, you rightly feel that something extraordinary is about to happen. The white dwarf has indeed gained a lot of weight, reaching 140% of the mass of the Sun, a mass threshold. The pressure in its own core suddenly becomes sufficient to trigger a new, astoundingly violent chain reaction that brings the white dwarf to an extraordinary demise. In the blink of an eye, it blows up. The explosion is 5 billion times brighter than the Sun. An impressive swan song. Such explosions are called Type Ia supernovae. They occur about once every century in any given galaxy. They are incredibly handy because they are all very similar. Identical, even, they always occur when a white dwarf reaches 140% of the mass of the Sun after feeding on another star, and hence they always shine with the same light, 5 billion suns combined into one little spot not much larger than our Earth. Much brighter than the Cepheids, they are ideal candles with which to probe the furthest reaches of our universe and to check Hubble's expansion law. Type Ia supernovae are so much brighter than anything else that, unlike Cepheids, human-made telescopes can single them out in faraway galaxies. Knowing their intrinsic brightness, as with Cepheids, scientists can infer how far away they are and how fast they are moving away from us. In 1998, two independent teams studying such distant supernovae published their results. One was led by U.S. astrophysicist Saul Perlmutter and the other by U.S. astrophysicists Brian Schmidt and Adam Rees. Both teams found out that about 5 billion years ago, after more than 8 billion years of normal behavior, the universe's expansion started to accelerate. The scientific community was shocked. And so should you be. Not only was it not expected, only the opposite results seemed acceptable. At large scales, it is Einstein's general relativity that rules everything, and Einstein's gravity, like Newton's, only allows for objects to attract one another. Whatever fills in the universe, be it matter or antimatter or dark matter, must hence, in the long run, slow down any expansion, not accelerate it. Perlmutter, Rees, and Schmidt's observations, however, said otherwise, and the only possible way out of this contradiction was for something very new to be introduced to account for such an acceleration. And this something had to fill the entire universe. And it needed to have an extraordinary property. It had to be acting as an anti-gravitational force, repelling matter and energy instead of attracting them. For some unknown reason, this new force overcame all the other large-scale forces in our universe about 5 billion years ago. Before that, its effect was zero. This rather puzzling energy has been called dark energy and, funnily enough, to account for its observed effects, there must be a lot of it. According to modern estimates, a tremendous amount, in fact. 3 times more than the dark matter. 15 times more than the ordinary matter we are made of. As a result of their discovery that our universe's expansion accelerates rather than slows down, Perlmutter, Schmidt and Rees were awarded the 2011 Nobel Prize in Physics, and the whole energetic content of our universe had to be completely reevaluated. Today, according to NASA's satellite estimates, it consists of the following: dark energy, 72%, dark matter, 23%. The matter we know, 4.6%, 50. Everything you've seen so far throughout your journeys corresponds to only 4.6% of the total content of our universe. The rest is unknown. Unlike dark matter, however, the existence of some form of dark energy had been postulated in the past. About 100 years ago. By Einstein himself. He had even called it his biggest blunder, although today it seems that his blunder was to have called it a blunder. You may remember, from part 2, that Einstein did not like the idea of a changing, evolving universe. He much preferred to think that time and space were, had always been, and will always be as he experienced them. Unfortunately, his general theory of relativity, in its simplest form, said otherwise. It said that space-time can, and does, change. To allow for the possibility of a universe that did not evolve, he found out that he could somehow change his equations by adding a new term, the only extra term they allowed. At the time, it was a bold gesture. Einstein's equations meant that the local energetic content of our universe is absolutely equivalent to its local geometry, so if one of these two can change, the other can too. Adding some new form of energy everywhere therefore changed the universe's shape and dynamic everywhere. By energy, Einstein meant everything that has a gravitational effect, which now includes matter, light, antimatter, dark matter, and everything else that has a normal, decent, attractive gravitational behavior. But the term Einstein added could have either effect, depending on its value. It corresponded, physically, to an energy that fills the entire universe. He called it the cosmological constant. Thanks to it, the universe could be static and well-behaved, abiding by his philosophical opinions. Relieved, Einstein could sleep again at night. About 10 years later, however, Hubble's work turned the expansion of the universe into an experimental fact. No more static universe. So Einstein withdrew his cosmological constant and called its introduction his biggest blunder. About 100 years later, it now appears, rather ironically, that what he erased on paper could be the much-needed tool theoreticians required to explain the largest mystery ever uncovered by mankind, the dark energy that drives the acceleration of our universe's expansion. The cosmological constant can make the universe the complete opposite of static, undergoing accelerated expansion. It could solve the dark energy conundrum. The only problem would then be to figure out its own source. We'll get back to that in part 7. In the meantime, I wish pretty much everybody could make blunders like Einstein's. Whatever it is, the idea of dark energy has already changed our vision of cosmology. Before Perlmutter, Rees and Schmidt's discovery, our universe was thought to have two possible futures, depending on its overall contents. Too much matter and its expansion was doomed to reverse at some stage, gravity overtaking it all, as if too strong a spring were attached to everything now moving apart. Within such a scenario, the whole universe would then contract. And everything would end in what was called a big crunch. It's like a big bang, but the other way round, with time fast-forwarded, not rewound. The other possibility was that there wasn't enough matter or energy to keep everything from moving apart. Perlmutter, Rees and Schmidt's introduction of dark energy says that this is the most likely future. Unless another surprise hits our telescopes one day, the chances are that this anti-gravity force field will make sure the expansion goes on forever, leading to very cold cosmic tomorrows. Both are rather gloomy perspectives, I agree. But as you shall see in the next and last part, that cold death may not be the end at all. Now, again, it is also possible that Einstein's theory simply does not apply at these enormous scales. In that case, we are not allowed to use his equations to infer the existence of dark energy. Just as Newton's ideas tried out next to a big star lead to erroneous orbits, Einstein's equations could very well drift away from reality at some stage. As of today, however, the chances are that dark energy is real, and there is even a possibility that it has a quantum origin. A very exciting prospect for all those who like to link the very small to the very big. In any case, whatever they are, dark matter and dark energy are a big deal. Newton's gravity helped us to find new planets around the Sun. Einstein's gravity has led us to mysteries far bigger, mysteries so big they may hold clues about, or keys that open doors to, unknown realms of our large-scale reality. With the necessary humility such discoveries impose upon us, it is now time for you to see why general relativity cannot be a theory of everything, and why it predicts its own downfall. 6 singularities. Remember the quantum infinities? Remember the catastrophic consequence on spacetime of an infinite number of particles appearing everywhere, all the time, in the vacuum of quantum field theory? To deal with it, scientists had to turn gravity off and make do with those infinities as if they weren't there, or by ignoring what lay in the smaller still. Then it worked extraordinarily well, as long as gravity was not quantum. Now, let's leave quantum stuff aside for a little while more. What about gravity on its own? Is it possible for the matter we know, the classical matter we experience on a daily basis, to have the same impact on the fabric of our universe? Can it make spacetime collapse in on itself? The answer is a definite yes. And this time we even see the result in the sky. The image of many very heavy marbles thrown on a thin rubber sheet works well here. Due to the bending they create, close-by marbles should roll closer to one another, creating a lump that bends the rubber sheet still further. With each new marble rolling down to join the group, the rubber gets more and more distorted. At some stage, either because all the marbles have fallen in or because the remaining ones are too far away, this should end. Nothing strange about that. But if the rubber sheet is soft like chewing gum, if it is not strong enough to hold the lump of marbles in equilibrium with its own tension, it may well keep bending and bending, even if no more marbles fall in, until it breaks. No material is strong enough to hold any weight. Hence the idea of a density threshold: put too much weight upon too soft a surface and the surface around the mass will distort and distort and distort, and eventually break. Now, what about space-time? Although it is not supposed to break, space-time reacts to very high densities in perhaps an even more dramatic way, because the fabric, in this case, is not rubber, but space and time themselves. Space-time. Not a flat cloth, a volume. Plus time. Space-time bends and curves and stretches around the objects it contains, be they matter or any other type of energy. That's Einstein's understanding of it. Keep piling energy into a given volume and, like the rubber sheet, you are bound to end up with a problem. Beyond a certain threshold, nothing will be able to stop the bending of space-time from getting steeper and steeper and steeper, even if nothing more falls in. As the bending gets worse, whatever started the bending gets squeezed, making the density in there even higher, a vicious circle that inexorably leads to a collapse of space-time, a collapse marred with infinities that general relativity cannot handle. Such infinities are called singularities. They are not the same as the quantum infinities you saw earlier. They have nothing to do with quantum processes. They occur when there is too much mass, or energy, in too small a volume. They are localized. And the possibility of their existence announces the breakdown of Einstein's theory of gravity. In the late 1960s and early 1970s, when pretty much everyone else was either high, listening to psychedelic music or looking for new fundamental particles, UK mathematical physicists Roger Penrose and Stephen Hawking proved, in a set of celebrated theorems, that such collapses necessarily happen within a universe ruled, on large scales, by general relativity. With their theorems, they showed that Einstein's general theory of relativity had the very humble characteristic of predicting its own downfall. Just as Newton needed a larger theory to account for Mercury's drift, it became clear that Einstein's theory needed to be expanded, if only to account for these collapses. Where do they occur? You wonder. Can they be found in nature, or are they merely theoretical fancies? They are real, and I know you know where to find them. One such singularity, the mother of them all, lies in the past of our universe, when our whole universe's energy was confined in a dramatically small volume. In a sense, our universe was born out of such a singularity, since it is out of it that space and time became what they are today. Another singularity lies deep within all the black holes that stud our universe. Contrary to what many may believe, black holes are the opposite of empty holes. They are born when, due to some catastrophic collapse, too much matter ends up being squeezed within too small a volume. As you will hear later, the death of a giant star can trigger such a process. The question that has both tormented and excited many brilliant brains ever since the Penrose, Hawking theorems, therefore, is this: since singularities apparently happen in nature, how can one even conceive of what happens within them? How can one even think about places where space and time do not make sense anymore? What theory can be used to probe those catastrophic collapses? A theory that involves both the very big and the very small. Since black holes and our universe's origin both consist of an enormous amount of matter and energy confined to a very small volume, the answer should involve a theory that mixes gravitational and quantum processes. Whatever theory we can find to understand our universe that is better than Einstein's, it has to include quantum aspects of gravity, i.e. spacetime. Penrose and Hawking proved that Einstein's theory of gravity has deep limits, that it cannot explain all of our universe, neither in the past nor as it is now. It breaks down before one can reach the birth of spacetime, and it breaks down before one can probe what lies at the bottom of today's black holes. That being said, one could think that all the blame for the difficulty of finding a quantum theory of gravity should be on gravity, on Einstein's baby. But you saw that that is not the case. There are problems with the quantum vision of the world as well. Still, however hard it may be, you are now about to try to mix them both, for it is time for you to probe a black hole. 7 Gray is the new black. Considering the situation, you feel extraordinarily normal. You are not ethereal, you cannot see through yourself, and your arms and legs and everything else in your body responds positively when ordered to move. You are flesh and bones and blood, and your heart beats the way it usually does. A slight pain in your neck seals it, you feel just like you do on Earth. But you are in outer space. Your robot guide, complete with its tinny yellow casing and tube for delivering particles, is right next to you, as tangible and real as you are. You look around. The futuristic airport is gone. You recognize nothing, but you guess you must be within a galaxy, near its center. Billions upon billions of stars are shining as they normally do. Everywhere. Except right in front of you, where a dark patch of space-time is devoid of stars. As you move alongside the robot, you realize that the area of darkness is drifting against the background stars. So it is close. A void hanging in space. A dark threat looming over one and all. You know what it is. It is huge, about 10 billion times the mass of our sun. But this black hole looks nothing like the one you saw at the center of the Milky Way. There is no ring of burning lights surrounding it. There is no nearby star about to fall in. This black hole has already gobbled up and digested all the stars that were once nearby. And pretty much all the debris as well. It is clean now. It has nothing to feed upon but the occasional incoming rocks deflected by some faraway misfortune. Some of them are on their way now. If even a hint of quantum gravity lies down there, we are going to find it, announces the machine. Is it going to be dangerous, you ask? Of course it is. It's a black hole. You look again towards the black hole, comparing it to the one you met at the start of the book. There is no jet of light bursting from its poles. There is just a rather circular, flat-looking black patch of emptiness. You are spiraling down the space-time slope it creates. As you fall, the images of faraway stars passing near to its edge look distorted, and nowhere near where they were a split second before. From being points of light, they become small strings of brightness covering the dark disk's outer edge. And then they vanish, as if swallowed by the dark emptiness, before reappearing on the other side where the distortion sequence is played again, but backwards, until they look like distant shining dots once more. Light, it seems, is distorted by this hole, a hole that apparently extends from within, like a dark well, while its rim acts as a distorting lens. With the robot by your side, you continue to spiral down. You are still rather far away from whatever the black hole is, but you already feel a sense of doom and you suddenly wish that whatever the robot intends to show you arrives soon, so that you can leave before it's too late, whatever too late might mean. Look over your left shoulder, says the robot, after a moment of silence. You turn around. A rock is aiming straight for the black hole. It is a spinning asteroid the size of a mountain. It shoots by with astonishing speed, about 100 kilometers away from you. You lock your vision on its dark silver surface, the only object moving against the black disk of the black hole. The apparent size of the rock shrinks as it moves away. It is now about the width of a peach held at arm's length. Now it is the size of a small, distorted nut, and then suddenly, as your spiraling fall brings you to the other side of the black hole, 2 images of the rock appear. One to your left, the other to your right. The distortion of space-time around the dark patch is such that light seems to be able to take several paths to reach your eye. The rock will soon fall through, says the machine, almost regretfully. Fall through, you inquire, all the more worried. What do you mean fall through? Through what? Through the horizon. The what? The black hole horizon. The limit of no return. You will see. Or you won't. No human or machine has ever been so close to a black hole, let alone inside one. There is a theory about what should happen down there. But it may be wrong. Crossing the horizon, we will be beyond what is known. Maybe we shouldn't get too close then, you suggest. Or maybe we should, responds the robot. That's research. We will have to take some considered risks. Where should I look for the horizon, then? Everywhere. Moving its throwing tube to the left and right, the robot alternately points towards two opposite places near the black hole's edge, towards the two images of the rock, and in between. Your eyes now moving from one image to the other, you wait for them both to continue their fall, to disappear through the horizon, into the hole. But by the time you've completed another full orbit, the small, nut-sized, silver-brown asteroid is still floating above the dark emptiness. Strangely, it doesn't seem to have changed in the slightest since last time you were above it. In fact, it doesn't seem to be moving or spinning at all anymore. It didn't fall, you shout, relieved that perhaps you're not doomed to be torn apart by a black hole today after all. It did, corrects the robot. It is not there anymore. Very funny. It is gone, insists the robot. Only its image remains. That is the distortion of space-time in action. Of space and time. Our time, yours and mine, is not ticking like the rocks. The asteroid is beyond the horizon. Its image is still on the horizon. That's how it is. As you take this in, another object races past you, into the void, a glittering stone this time. It almost looks like an enormous diamond, and indeed that is exactly what it is. For some stars, when they die, can leave behind diamonds the size of a moon. As you watch it fall, you complete another circuit around the black hole, and you realize that you are much closer to it than you were before. And moving much faster. Turn after turn, the asteroid's several images, with the diamonds now next to them, all seemingly frozen above a surreal darkness, become more and more distorted. And so does the rest of what you can see. Whatever your eyes might be telling you, the robot is right again, the asteroid and the diamond are both absolutely beyond retrieval. And the black hole grew in size as it swallowed them both. Or at least its horizon grew. Is that what you wanted me to see? You ask the robot. That an empty hole grows as it swallows stuff? Black holes are not empty at all, replies the robot ominously. In fact, black holes are the polar opposite of empty. They are what happens when there is too much matter and energy in too small a space. To create one, tremendous energy is needed. As far as we know, only the most immense of shining stars release sufficient energy, at their death, to compress their heart into one. You encountered white dwarfs earlier on in your journey, and white dwarfs are the results of similar compressions, but they are not as extreme as black holes. All types of such remnants of stellar collapse are impressive, but black holes are beyond them all. And while we're at it, as you spiral down a couple more times around the black hole towards which you are inexorably falling, let me give you another reason why they are quite so frightening and mysterious. Were you to sit on any object in the universe, be it a rock or a planet or a star, you'd be able to send some light away to signal your position. But the denser the object you were to be sitting on, the more energetic your signal would need to be for it to climb up the slope created by the object in the space-time around it. It is just like with the salad bowl, the deeper it is, the faster you need to throw a marble from the bottom for it to roll all the way up and out. Sitting on a planet, a star, or a white dwarf, you need successively more and more energy for a signal of yours to escape their pull and reach outer space without falling back. Black holes are even worse. They contain so much matter and energy, and therefore create a space-time slope so steep that anything clumsy enough to approach them too closely is doomed to fall in. According to general relativity, nothing, in our universe, then has enough power to escape the black hole's gravitational grip. Not even light. The point of no return beyond which nothing can ever come out the black hole's horizon lies where the images of the rock and the diamond appear to be frozen when looked upon from way outside. The darkness keeps growing in front of you, as if a huge mouth was ready to swallow your reality. The distant stars, everywhere, now look very different. You even have the confusing sense that what you are seeing ahead of you actually lies behind. Turning your head around, you realize that it is not just a feeling, it is actually the case. The light emitted by the stars shining behind you, traveling as fast as light always does, overtakes you and shoots by the slope created by the black hole. Whatever rays propagate to the left of the monster reappear to its right after having made a roller coaster-style U-turn behind. And then these lights shoot towards you and hit your eyes. Looking forward, you are also seeing behind you. From where you are, in fact, you can see the entire universe just by staring ahead. And as you keep spiraling down, things get more confusing still. The images of the rock and the diamond are now moving again. As you get closer to them, your time and theirs get closer, and they suddenly vanish altogether. You've just seen them cross the horizon, something they probably did hours ago, according to their own watch. Next to you, the robot has turned around, its throwing tube now pointing towards outer space. You slowly turn around too, fearing what you might find. And what you see is beyond the imagination. All the stars, everywhere, which a second ago seemed to be so still, are now moving. Their lack of stillness, normally unnoticeable even over the span of a human life, is now apparent to you. From the closest ones to the furthest, they all shoot through space and time. Some of them are so fast-moving that they even leave a trail on your retina, drawing evanescent curves of light across your image of the universe. Just as, when you were traveling closer and closer to light speed earlier, shooting through the universe, you watched an astronaut's life, and her children's children's race past, their time accelerated compared to yours. Back then, your time and theirs were different because of your speed. This time, it is all due to gravitation, to the bending of space-time caused by the black hole's presence. For here, around the black hole, your time flows slower than it does everywhere else. You are watching the future of the universe as it unfolds, and this is again what is meant, in practice, by space and time being united in space-time. Have we crossed the horizon? You suddenly ask, worried. Are we doomed to fall in forever? The robot turns around again, to face you, and you realize with great surprise that its throwing tube has widened. In fact, it looks as if it wasn't made to throw particles anymore, but bowling balls. We haven't crossed the horizon yet, no, it replies. But you are about to. If you didn't know better, you'd say that you detected a hint of delight in the robot's voice. But before you can react, it fires a heavy ball straight at your chest. Unable to avoid it, you have no choice but to grab the projectile. Instantly its velocity pushes you downwards, towards the gaping darkness. You shout, you frantically try to grab something to stop yourself from falling, but there's nothing around to hold on to. You fall. The robot is moving away. A second of yours already corresponds to a minute of its. And now an hour. And now a day. And now a year. As the robot recedes into the distance, millions of years pass before you. Stars explode. New stars are born. And you see it all. Billions of years out there are now gone. Another galaxy merges with the one you are in. The robot is nowhere to be seen anymore. You are on your own. And you panic. You have crossed the black hole horizon. Dumbstruck, you watch the future of everything. Gripped with fear, unable to focus, you fall feet first, eyes locked above your head on the unfolding life of the whole universe, while you disappear into an abyss of unknown nothingness at the bottom of which lies a singularity. And now you turn around to stare into it, into the black hole's mysterious heart, where the opposite of nothingness, the very matter that creates all this nonsense, should somewhere create this absurdity. To your great surprise, you do not see anything at all. Not even your body. No feet. No nose. Not even your own hand. Light may fall upon you from above, from outside, but nothing rises from down there, from any direction whatsoever, however close. Light hasn't enough energy to do so. You have crossed the black hole horizon and you are now doomed to forever plummet towards the surface of many collapsed star cores reunited in an endless imploding fall, until they stretch space-time too much for Einstein's general relativity, with consequences unknown. In fact, were you to really be there, you'd be dead, for if even light cannot make the tiny journey from your feet to your eyes, there's no way your blood could climb up the space-time slope you are sliding down to reach your brain. But since we still have much to see, we'll assume you are still alive. Reluctant to stare into this bottomless darkness, you decide to turn around again, to look at the universe as its images flow down towards you, through the now distant horizon. But you can't. Any movement that involves having part of your body budge up, towards the above, the outside, is prohibited. It would require an energy that even light does not possess. No upward movement allowed. As you begin to wonder if anything could be worse than this, tidal forces begin to make your body ache. The gravitational effect of the black hole's invisible presence is now starting to drag your feet down more than your arms and head. The black hole's gravity is stretching your body. You are going to end up strung out like spaghetti. Even if the treacherous robot had equipped you with the most powerful rocket thrusters ever invented, it would not have changed a thing. Whatever the engine, were you to try moving upwards from within a black hole horizon, you'd feel like you were powering along on the slippery, stretching fabric of space-time, as if exercising on an endless running machine whose speed always exceeds yours, by a huge margin, dragging you back. According to Penrose and Hawking, you are being pulled by the space-time singularity that lies down there somewhere, a singularity that will never be seen from outer space. No light being allowed to escape the horizon, the singularity is hidden by it. Down there, the very notions of space and time break down, just like at some time before the Big Bang. No one could ever look into the heart of a singularity and emerge to tell the tale. Such places, it seems, must remain forever cloaked. According to general relativity, neither you nor any atom that belongs to you will ever get out of there. A sad thought, especially now that you are completely torn apart, reduced to a long filament made of all the particles that constituted your body. A sad thought, yes, but general relativity should not be trusted down there. For we must remember that general relativity is not a theory of quantum fields. And the moment this thought occurs to you, hope immediately returns to your mind and you turn yourself into your mini-you state. And you wait. At first, nothing happens. And then, surprisingly, you see all the elementary particles you were made of disappear. Or jump, to be more precise. Quantum jump, in fact. And now they are out. Out of the black hole, where, rather fortunately, they reassemble into a mini-you. And the robot is there to meet you. At this point you are tempted to lunge for it and attempt to break off its metallic tube for having fired you through the black hole horizon, but before you can act the robot's metallic voice announces. I've been waiting for you for about 10 billion years. I'm glad you recognize me. You suddenly don't have the heart to hurt it anymore. And besides, there are more important things to think about. Not least the fact that what you have just experienced is an instance of gravity and quantum fields interacting with each other. All around, the stars are again moving imperceptibly slowly. 10 billion years really have passed since you crossed the black hole horizon. You look at the black patch of space from which you miraculously escaped. At first glance it doesn't seem to have changed a bit, but now that you know what to look for, it is as if yet another veil has been removed and you really see. Particles are escaping the black hole, moving away from it, radiating, as if the dark monster were evaporating. Maybe this was happening all along, you realize, but you just hadn't noticed it. But how can that be? As Richard Feynman once said, one only really understands a phenomenon when one can give many different reasons for it to happen. So, while you and the robot watch the particles shower out into space, I'll give you 4 reasons why black holes are leaking particles. They are all linked to a process you've already encountered. The first one is the simplest. Quantum particles can borrow energy from their field, as you know. And they can do that when inside the black hole horizon too. With this borrowed energy, they are allowed to move faster than light for a little while. Not for long, but for long enough to quantum jump out of the black hole's no-return zone. That's what you did as your mini-you. This is a quantum process. All the ways to understand what happened to you are quantum in essence, so they all come with the usual health warning, for like so much of what you have seen in the quantum world, they might sound absurd. The second reason is no exception. You could say that all the particles that fell through the black hole horizon also did not fall through it. Did, and did not. Out of all the possible paths a particle might take to fall in, most of them are a miss, because there is more space outside the black hole than in it. Amazingly, this idea, worked out carefully, makes the black hole evaporate in the exact same way as the first reason above. A third reason goes as follows: due to the horizon that separates them from one another, the vacuum inside the black hole horizon is different from the vacuum outside, so that some form of vacuum force, a Casimir effect, should push the horizon inwards, making the black hole shrink and evaporate. This again, rather miraculously, gives the same result as above. The fourth and last reason I'll give here is that particle-antiparticle pair creation occurs near all black hole horizons, with antiparticles falling in more often than particles, just as more often than not there are more particles than antiparticles around us. Having crossed the horizon, the antiparticle is then bound to end up annihilating with a particle there, making them both disappear, while only a particle remains outside, the particle that was created with the antiparticle, the twin of the particle that got annihilated inside. Again, this gives the same result. These are all quantum effects you've witnessed before, but they are here applied in the vicinity of a black hole. And they all lead to the same conclusion: black holes evaporate. They leak stuff. As you now watch the black hole shine, therefore, you realize that this cosmic monster of a black hole, which had been swallowing entire stars for eons, is not black anymore but gray. And shrinking. Even more surprising is the fact that the more particles it shoots out, the hotter it seems to become, and the hotter it becomes, the more particles it shoots out. A vicious circle that should inexorably lead to its death. The death of a black hole. Unbelievable as that might sound, the black hole you are watching is shrinking and emitting some radiation. The energy space-time stored within it by swallowing whole worlds is now given back to outer space, a particle at a time, as if, like radioactive decay, black holes were around to break things down, to give the particles a second chance. All the quantum fields of nature, excited by what is nothing less than the most powerful gravitational object known in the universe, are now using this unexpected bonanza to stuff themselves with energy. As the black hole gets hotter and hotter, their fundamental particles that had until now lain dormant, wake up and shoot away. You see it happening. And the smaller the black hole becomes, the higher the field's excitation, the more energetic the particles shot away. Gravitational energy is transformed, once again, into matter and light. As all this unfolds before your very eyes, you realize that it is most contrary to earthly principles. A mug of hot water, on Earth, doesn't heat up as it evaporates. It usually cools down. Were it not so, forgetting a hot coffee on a table would lead to disaster. The evening news would be filled with stories such as, "Yet another cup of coffee ignites a table, setting a whole building on fire." Remember to always dispose of your hot beverages in the appropriate bins. Black holes are apparently different from cups of coffee. The more they evaporate, the more they shrink, the hotter they get. No one knows what happens at the end of this process. Do black holes disappear with a final bang? Does a weird, tiny remnant with peculiar properties stay behind? To figure out an answer, one would need to know what laws rule the singularity that hides deep within. Scientists have been searching for such laws since 1975. It was in that year that Stephen Hawking discovered, on paper, that black holes evaporate. At first, he did not believe his own calculations. Light appeared to be coming out of a place where no light was supposed to shine at all. So he did his calculations again. And again. Only to see that light and particles really did manage to find their way out of black holes. He published his finding in the journal Nature and instantly became famous all around the world, beyond scientific circles. Quantum effects made black holes evaporate. Whatever falls in is not doomed to stay inside forever. It gets out, although not in a recognizable way. Being able to evaporate, black holes therefore do behave as if they have a temperature that is today known as the Hawking temperature. As you watch the black hole shine the last of its energy away, you realize that what you are looking at tells you that the very big and the very small do talk to each other, as of course they should. Black hole radiation is the only proof so far that our theories might reflect nature in that respect. It is the hint that says a theory of quantum gravity might be possible after all. Any serious contender to such a status will have to predict the Hawking temperature and black hole evaporation all the way through to a black hole's death. Black holes can die, you say out loud in disbelief. Like everything else in this universe, says the robot. But around the end of the 1970s, Hawking's discovery also led to a very strange and rather unnerving statement. With his temperature formula in hand, he tried to extract and decipher, out of the radiation he had found, some information about what made a black hole in the first place. To make things easier, he started with an already fully formed black hole and threw in different materials, to see how they each might be affected by the subsequent radiation. Amazingly, there was no difference. Nothing within the radiation emitted told him anything about what he had sent in, apart from their mass. It seemed, from what he could tell, that black holes purely and simply bleached out all the characteristics of what they had swallowed. Except the mass, that is. Whether a few humans, a bunch of books or a rock or a diamond were to fall through a black hole horizon, if they happened to have the same initial mass, they would later be evaporated in the exact same way. For black holes, it seemed to Hawking, humans and books and stones all tasted the same. For all of us, this means that as far as black holes are concerned, only our mass has any meaning, which may strike some as being a bit reductive. For scientists, however, this was a philosophical catastrophe. Until Hawking's work, black holes were supposed to gobble up everything that crossed their horizon, and grow, and this was not a problem. Anything that falls in isn't lost. It is just stored behind a horizon and difficult to retrieve from outside. With black holes evaporating bleached information, we are confronted by a troubling realization: things start to vanish from reality. Hawking radiation 51 being independent of what falls in, these dark monsters become memory blackouts for our universe. And once black holes have evaporated their past away, what they stored is not merely difficult or impossible to access, it just isn't anywhere anymore. It is gone. Science was looking for a theory of everything, a theory to explain it all in one single formula, and the first result reached through such an attempt dealt a hell of a blow to science as a whole. Science, forever unable to account for such lost pasts that occurred in black holes, was told to give up on hoping to one day describe and understand our universe's entire history. Hawking radiation was not a bell tolling the end of quantum physics or general relativity, but the end of physics as a means of learning where our universe came from. This problem has been dubbed the black hole information paradox. Today, physicists are more familiar with the crude approximations Hawking used to reach his result. But 40 years after his discovery, when Hawking asked me to work on it with him, the problem remained shrouded in mystery. But there are now hints that a way out may have been found, for if we apply what is known about the quantum world to black holes themselves, then black holes could be there, and not be there. Where such ideas have led scientists is what you will discover in the next and final part of this book. For now, however, from some unknown billions of years in the future, you suddenly remember the robot's suspicious happiness at seeing you reappear out of the black hole. Didn't you wonder at the time why it was so pleased that you recognized it? You thought it was genuine, didn't you? But it probably wasn't, and you now know the reason. The robot wasn't sure whether you'd remember anything at all. It didn't know if the black hole would or would not bleach your body and mind clean of all the information they contained. Then you recognized it, wanted to break it to pieces for having pushed you, and it knew. It knew that you remembered it all. That information was not lost in your case, even though you did not have the slightest recollection of flying backwards through the black hole horizon. You remember becoming a set of fundamental particles. And then being out. In between, a quantum jump occurred, or something else. Figuring out how precisely this could have happened is what a decent theory of quantum gravity is supposed to achieve. And since this is what you will soon start exploring, let me emphasize the fact that since the beginning of this part of the book, you've entered a very theoretical world. Dark matter has never been created in the lab, and nor has dark energy, and the same holds for black holes. Their evaporation hasn't yet been detected by any experiment, directly or indirectly. Hawking would have received the Nobel Prize otherwise. Black hole evaporation, for one, is rather hard to detect. How hard? Let's see. Take the sun. To turn it into a black hole, you'd need to squeeze it into a sphere 6 kilometers wide. That's equivalent to about 2/3 the diameter of London. 52 Most black holes, throughout the universe, are born when giant stars die, so they should be bigger than that. Now, let's assume that one of these solar mass black holes has swallowed everything that surrounds it and now lingers quietly somewhere, far away from everything. Its radiating temperature, its Hawking temperature, should be about 1/10,000,000th of a degree above absolute zero. A 10,000,000th of a degree is not much. It is hard to measure in its own right. But that is not the main problem. The main problem is that it is far less than the 2.7-degree hot cosmic microwave background radiation that bathes everything in our visible universe. As a result, solar mass black holes are not seen as evaporating now. In fact, to date they have never been seen to do so. They are and have always been masked by and feeding on the background leftover heat from the Big Bang era. And since the heavier the black hole, the lower its temperature, it gets worse for the large, supermassive monsters that sit at the center of most of our universe's galaxies. Their Hawking temperature is even cooler than solar mass ones, not to mention that they are surrounded by extremely hot rings of infalling matter. What would get Hawking a Nobel Prize might therefore lie in the world of the very small, since tiny black holes there should be very hot. Unfortunately, we still have a problem. Scientists are pretty certain they've spotted giant black holes, but they've never seen any tiny ones. Never mind, though. Let's assume they are there. Could we make anything out of them, in practice? To figure this out, let me introduce a small parenthesis that will shed some light upon what I earlier called the Planck wall. At the beginning of the 20th century, one of the most impressive scientists of all time founded what we today call quantum physics. He was German, like Einstein, and his name was Max Planck. He received the Nobel Prize in Physics in 1918. From his own discoveries, Planck understood that there was a scale beyond which quantum effects could not be neglected. Take a large object, and everything is fine. Newton's understanding of nature can be applied to it, and whatever is expected of it corresponds to the reality we are used to in our daily lives. But shrink that object to smaller and smaller sizes and Newton's vision starts to fall apart. Newton, let me say once again, figured out a way to describe the world at a scale we are familiar with in everyday life. It agrees with our common sense. For the world of the very big and energetic, Einstein's vision has to take over. For the very small, it is Planck's. There, we must consider the quantum world. And there is a constant of nature that allows us to estimate when this occurs. It is called Planck's constant. Planck's constant is on an equal footing with two other universal constants of nature, namely the speed of light and the gravitational constant, which tells us how two masses attract each other. One day, Planck started to play with these constants, and he built three things out of them. One was a mass. Another was a length. And yet another was a unit of time. The mass turned out to be of 21 micrograms, 21 millionths of a gram. It is called the Planck mass. The length was 1,000th of a millionth of a billionth of a billionth of a billionth of a meter. It is called the Planck length.